Hello students, we shall be discussing about the fourth practical, that is to determine the resistance of a galvanometer by half deflection method and to find its figure of merit. The apparatus we are going to use is a Western type galvanometer, a voltmeter, a battery, a rheostat, two resistance boxes. One should be a small resistance box which will be called the shunt resistance, and the other is a bigger resistance which we are going to connect in series. We shall be talking about the connections in the following lecture. Then we need two one-way keys. We need a meter scale, some connecting wires, and a piece of sandpaper to rub the wires before connecting them, because sometimes they are corroded, and because of which the resistance of the connecting wires will increase. We shall also look about two circuits here. One is the first one in which we are going to find the value of the resistance of the galvanometer G. We are going to calculate this G. And the second circuit will be used to find out the figure of merit. The two formulas which will come in the experiment, which we are going to use in the experiment, and I'm going to show how this formula has come, and that can be a question in the Viva also, that how did this formula come and what is the mechanism behind this thing. The first one is to find the resistance of the galvanometer, that is R into S upon R minus S, where R is the resistance box, the big resistance box, and S is the shunt resistance which is connected in parallel with the galvanometer, divided by R minus S. This is the first formula by which we shall be finding out the uh, resistance of the galvanometer G. We will be finding the value of G. Then the second formula that we shall be using is the figure of merit, that is K. K is equal to E upon R plus G divided by theta. So for that we shall be using this particular circuit. I also want to tell you what the figure of merit looks like, or what the figure of merit actually is. Figure of merit can, in layman's terms or in simple language, be termed as the least count of the galvanometer. Very simple definition. Or I can say, what is the reading of one small division of a galvanometer is called its figure of merit. Alright, so let us see how the circuit looks like and how are we going to get these two formulas from the given circuits. This is how the circuit will look like in real life. As said before, I'll just show you the connections. From the battery we are connecting this big resistance box R. This resistance box is in series with the galvanometer. So positive of the battery, positive of the galvanometer. Then the negative of the galvanometer is connected to the battery. So you can see this is a series circuit. Then there was also a shunt resistance. So this is the shunt resistance, and it is connected in parallel with the galvanometer, you see. This is the first connection, first terminal, and then the second terminal. So S and G are both parallel to each other. So I hope you could understand how the connections are to be made in the circuit. Let us now understand that how did the formulas come. The first formula was G is equal to R minus S. So two formulas we are going to talk about. The first is we shall also be talking about the two formulas. The first one is G is equal to R into S upon R minus S, and from the another circuit diagram we got that K is equal to E upon R plus G into theta. What knowledge we should already have before starting this experiment is that the current flowing through the galvanometer is directly proportional to the deflection in the galvanometer. So I is equal to K into theta, where K is the figure of merit. There is the number of, or that is the twist per unit turn, and this is the total turn. So that will give you the value of current. So I is equal to k theta. This is the formula that we have derived in galvanometer. I shall also be further uploading a video where I'll be talking about what kind of Viva questions will come, but that will come uh, after all the experiments are covered. So these are the basic things we need to know, that the deflection and the current are proportional to each other. That is, the current flowing through a galvanometer is proportional to the deflection of the galvanometer, and K is the figure of merit. Alright. Now let us understand how did the first formula come. For that, I am going to switch on this key first. K is on. This is the eliminator. Say the current I is flowing in the circuit, and the maximum current that can flow through the galvanometer is Ig, and this key too is open. So as of now, no current is flowing in the shunt circuit. I mean, there is no current flowing through this circuit, the shunt. So the galvanometer is going to show some deflection when the current flows through it. So what will be the deflection of the galvanometer? So I'll be taking I is equal to k theta. This is the first equation. Now I have also noted down the deflection. This is the first deflection. Now why this method is called half deflection method? Because the second time when we are going to connect this circuit and we are going to adjust the value of shunt, so that the new deflection of the galvanometer comes out to be theta by 2. That is why half the deflection, that is why we call it as half deflection method. So why are we doing that? We'll understand that in the course of time. So now let us correct this key also. Let us close this key. Now what will happen? Some current is going to, now the current I is coming through the circuit, and it is going to get splitted at this point into IS, and this will become IG. So I is getting splitted into IG and IS. I don't want to keep the variables, too many variables, so I can write by using Kirchhoff's law that I is equal to Ig plus Is. The actual formula would have been I minus Ig minus Is is equal to 0, because Kirchhoff's law tells us that the current entering will be added and the current leaving from a junction will be subtracted. So from this we are going to get I is equal to Ig plus Is, or I can say Is is equal to I minus Ig. So I am going to replace Is with I minus Ig. Alright, now we have adjusted the value of shunt in such a way that the galvanometer is showing half deflection. That means now the current in the galvanometer has changed. So how much is the current in the galvanometer? New current in the galvanometer, I am going to mark it as I dash G. I don't know how much is the I dash G going to be. So we know from the combination of resistors, I'm just going to quote an example and I hope that will make some sense. Suppose we have two resistors. One is say 3 ohms, other is say 2 ohms, and the current of 6 ampere was passing. Now the current is going to get splitted into these arms. And how is the current going to get splitted? The current will always choose the path of least resistance. That is, more current will pass through the smaller resistor 2 ohm and less current will pass through the bigger resistor 3 ohm. So in how many parts is the current going to get divided? it is going to get divided into 5 parts, 3 into 5 parts. How much is the current going to flow through this? Now you have to take in consideration that less current is going to flow in this thing. So it will be 2/5 of 6 ampere, and here it is going to be 3/5 of 6 ampere. That means current is getting divided in the ratio of 2:3, where 2 parts out of 5 parts is going in the first resistor, that is the bigger resistor, and 3 parts out of 5 parts is going in the second resistor, that is the smaller resistor 2 ohm. So 2 ohm will get more current. Now instead of 2 and 6, I am going to change the value slightly, and that will make more sense to you people. I am going to take this value as I. This is the value of Ig dash. I am taking it as Ig dash because now the current Ig is not flowing through the galvanometer. You have taken the current such that the deflection in the galvanometer has now become theta by 2. And this is the current going through the shunt resistance Is, which is I minus Ig dash. So if I ask you now, okay, this resistance is say G and this resistance is S. So how much is the current going through G? So I'll be saying the current going through G, I dash G, will become equal to total parts is G plus S, and lesser amount of current is going through the galvanometer, that is S upon G plus S into I. As I said, if G would have been 2, S would have been 3, total parts would have been 2 plus 3, that is 5 parts. And how much current would have gone through 2 ohms? It would have become 3/5. How much current would have gone through the 3 ohm resistor? That would have become equal to 2/5. The same thing I am doing here also. Instead of 2 and 3, I have G and S. And that is how I will be getting the value of new current I dash G. Now this I dash G, that is the current, new current through the galvanometer, is causing the deflection in the galvanometer, and I am going to adjust the value of S such that now I dash G is coming out to be K times of theta by 2. K times of theta by 2. And it is how much value of I? It is I times of S upon G plus S. These are the two things that you have to take into consideration when you are doing this thing. Now, how did we get that first formula? In the first case, how much was the current flowing through the circuit? How much was I in the first case? That is, we are going to talk about the first equation and the second equation. In the first equation, we got the current flowing through the galvanometer was I only, because there was only one path for the current to flow. I and Ig were same. So I was equal to K theta. This was my equation number 1. And the second equation now I have got is I dash, that is the current flowing through the galvanometer, is equal to S upon G plus S times of the current flowing in the circuit I. That current I which is flowing in the circuit is getting divided, and this much current is going through the galvanometer. How much was I in the first case when the key K2 was open? So I is equal to V by R. How much was R? E upon R plus G. So how much is the value of this I when the galvanometer was showing theta deflection? It was equal to I is equal to V by R. How much was the R when only this circuit was functional and key K2 was open? The total resistance was R plus G. So how much was the current at that point of time? This I was equal to, so this I is equal to E upon R plus G is equal to K theta. This is my new equation number 1. Now, second case. How much was the I in the second circuit when these both were also connected? Since now there are 3 resistors in picture when key K2 is also connected, that is R, and G and S are in parallel with each other. If G and S are parallel, what is going to be the equivalent resistance of G and S? So this is, we know that 1 by R equivalent in parallel is equal to 1 by G plus 1 by S. If I take the LCM, it will become G plus S upon GS. if I take the reciprocal to find the equivalent resistance in parallel, it will become Rp will become equal to Gs upon G plus S. This is the equivalent resistance of shunt and the galvanometer, and this equivalent resistance is in series with the resistance box. So what is the R equivalent, new R equivalent now? Then R equivalent will become equal to Rp, there is this value, plus R. So that is going to be my new resistance. So how much is this I? Now here I is equal to E upon, how much is the new resistance? The new resistance on connecting G and S and R is R, and the equivalent of this is in series with R. How much is the equivalent? Gs upon G plus S. So it is R plus Gs upon G plus S. If I take the LCM in the denominator, I will become equal to E times of G plus S, because I've taken LCM in the denominator, and denominator goes to the numerator. So this will become R times of G plus S plus Gs. This is my I. Now how much is I dash? Substitute this value A in equation number 2. So how much will the value of I dash become now? I dash is equal to S upon G plus S times of I. This is new I, that is when the shunt is also connected in parallel, that is E times of G plus S upon R times of G plus S plus Gs. This G plus S and G plus S will get cancelled, and this I dash is nothing but it is K theta by 2. This I dash was the current through the galvanometer in the second circuit, which was some fraction of I, because some current was flowing through the shunt also. Now the deflection in the galvanometer has become half of the original deflection, and we know this relation that I is equal to K theta. So I'm going to rewrite this equation again, and I'm going to write it as K theta by 2 is equal to S into EMF upon R times of G plus S plus Gs. This is my new equation 2. This is my new equation 1. I have to find out the value of G. So I'm going to divide these two equations. So what am I going to get? Let us see. So I'll be getting K theta upon K theta by 2 is equal to E upon R plus G, E upon R plus G divided by S E upon R times of G plus S plus Gs, which I can rewrite as K gone, theta gone, 2 is equal to E upon R plus G multiplied by, now I'll have to take the reciprocal, R times of G plus S plus Gs upon SE, E and E gone. I'm going to multiply the denominator, that is what is left, R plus G and S is left. I'm going to multiply it there. So it will become 2 times of S into R plus G, and open the bracket here, it will become RG plus RS plus GS. So it will become 2SR plus 2SG is equal to RG plus SR plus SG. I'm just renaming it so that we can easily group the terms. I need to find G, so I'm going to group the terms of G on one side. I'm going to bring this term here, and I'm going to take the rest of the terms there. So it will become 2SG minus SG is equal to RG plus SR minus 2SR. So it will become SG is equal to RG minus SR. There is a G here also, there is a G here also. So I'm again going to group the terms together, and SR I'll be taking on that side and SG I'll be taking on that side. So it will become SR is equal to G times of R minus S, which implies G is equal to the formula which we were longing to derive, that was G was equal to R into S upon R minus S. This is the formula which we had been trying to determine or trying to derive. R into S upon R minus S. This is how the formula comes out. Now in the practical, you don't have to derive the formula. I just gave this introduction so that you understand how did this formula come into picture. So this is very, very simple how to find this thing out. And the second one is to determine the figure of merit. To determine the figure of merit, we have already determined the figure of merit from the first equation, this equation. Just use this equation and we'll get the figure of merit. You see, I have to find K. So how much is K? So K comes out to be E upon R plus G times of theta. This is the figure of merit. So calculation of figure of merit is very, very easy. That we can do by using the first circuit only. That means we have to just use the above circuit, this circuit. That's it, nothing else. So here I is equal to E upon R plus G, and we know that I is equal to K theta. That is the principle of how a galvanometer works, or that is the thing that comes out in a galvanometer, that current is proportional to the deflection of the galvanometer. So I is equal to K theta. So that formula we have used here, where I is equal to E upon R plus G, and I is also equal to K theta. So K will come out to be E upon R plus G into theta. The second part of the experiment is very easy to determine the value of figure of merit, and to determine the deflection of the galvanometer, G is equal to R into S upon R minus S. Was a little complicated. It's actually very fundamental. So if at all somebody asks you and you are able to grasp this thing, I hope you will be able to crack the Viva also. So now let us get back to the table, that what we actually have to do. Now we have two formulas in mind. Even if we do not know how the formula has come, that will hamper our Viva. And if even without knowing the background also, just by knowing the formula, we can do the experiment. So I'll show you how easily the experiment can be done. You see how to make the table. We know two formulas now. One is G is equal to R into S upon R minus S. First we'll take the serial numbers. Then we shall be taking out the resistors from the main resistance box R and calculating the value of the deflection of the galvanometer. So we shall be getting the deflection of the galvanometer. These readings will come into picture. Theta. Then we are going to take out the resistance from the shunt, and what we shall be getting is half the value of the deflection. Now you see, when I have taken resistance of about 4500 ohms, the deflection in the galvanometer comes out to be 30. At the same time, now I'm going to take out the resistance from the resistance box X, that is the shunt resistance, and here the deflection is coming out to be 15. So this is half deflection. When I'm getting 30 for some value of R, I have to choose some value of S such that the deflection comes out to be half of it. So this is 30, this is 15, and so we have got R 4500, we have got S, so the value of G comes out to be RS upon R minus S. That's it. So even the theta which is being calculated is not coming into picture in the calculation part. In the calculation part, that is not coming into picture. So that is a good thing. So in the same way, we have to take about 3 sets of readings or 4 sets of readings. Now you see, in the second case, the resistance box, the resistance taken out of the main resistance box R was 9500, for which we got a deflection of say 14. Now we have taken out this resistance in such a way that the shunt resistance is chosen in such a way that the deflection now comes out to be half. Here the deflection was 14. For some value of S, the resistance the deflection in the galvanometer now comes out to be half of it, 7. So we know the value of R, we know the value of S. So using this value of R and this value of S, for which we got full deflection and half deflection, we can calculate the value of G, find an average for that. As simple as that. To find the figure of merit, we just need this formula. The same thing we shall be doing. The same data we are using, but we do not need this data. We just need the resistance box R, we need the deflection of the galvanometer theta, and we need the value of deflection, resistance box, and theta. That's all. So first case, we have taken the EMF, we have taken out the resistance from the resistance box. Deflection say comes out to be 30, as we have taken in the first case. Only the same table can be used, and K comes out to be E, which is here as we have taken say 3 volts upon R plus G. R we have already got, and G we have calculated from this data by taking the mean of this data. We have got some value of G, so that value of G we are using here. R we know is 4500, G say here we have got as 70.8, and theta we have got as about 30 divisions. So put the value and you will get the value of figure of merit. Again you have to find the average of this. So that is how the experiment goes. So just by knowing the value of R, you calculate some random value of theta, adjust the value of shunt in such a way that the deflection of the shunt comes out to be half. Use this value of R, this value of S, and this formula G is equal to RS upon R minus S. You will be getting the value of the resistance of the galvanometer. Take the average. Now come to the formula for finding the figure of merit. The figure of merit is found out by using the above circuit, the second circuit, this one. So this circuit, we know that E upon R plus G will give you I, and I is equal to K theta. So K comes out to be E upon R plus G into theta. So there are certain unknowns here. First unknown is say E. So E we have got by using the battery eliminator. R we have got by using a suitable resistance. Theta we have got by measuring the deflection of the galvanometer. Just put the values, take 4 such readings by changing the value of R, and you'll get the mean of it. So this is how you'll be doing the experiment. I hope you have understood this thing. Certain precautions are to be taken care of. That means all plugs in the resistance box should be tight. The EMF of the cell should be constant. Initially, a high resistance from the resistance box should be introduced in the circuit. Otherwise, for small resistance, more current will flow through the galvanometer and ammeter and damage it. So take a bigger resistance, so that, because you are not aware. So if you take a bigger resistance, less current will flow through the galvanometer and galvanometer will not get damaged, because we know that the galvanometer always measures very small amount of current. It is a current sensitive device, not a current measuring device actually. So first of all, you take bigger value of resistance, so the galvanometer gives you less deflection. So after that, you will be getting an understanding or an idea of what kind of resistance is to be taken out. Also, what are the sources of error that can come into picture? There is plug the resistance boxes, and plug of the resistance boxes should be cleaned. It should be tight, and the screws can be loose. The wires can be loose. The wires might not be clean, and the EMF of the battery might not be constant. I tried to wrap up this thing as short as possible. If you need any sort of further help, please write in the comment box below. If you have any doubt, please ask in the comment box below. If you like the content, please like, share and subscribe. Thank you.